Hello, everyone. You're listening to Uncomfortable Truths with Euclid Phoenix, where I talk about politics, religion, and other BS that I find interesting. For the BS part of the show, we'll talk a little astronomy, more specifically, white holes. Black holes are now firmly part of astronomy. We've imagined them, measured them, and even detected their collisions through gravitational waves. But what if there were objects that did the opposite? Instead of swallowing everything, they spit everything out. These hypothetical objects are called white holes. In white, they've never been observed. They emerge naturally from the same equations that predicted black holes. So what are they? And do they have any real place in astronomy? What is a white hole? A white hole is essentially the time reverse of a black hole. A black hole pulls matter and light inward. A white hole would eject matter and light outward. Nothing could enter a white hole. Everything would be expelled. The idea comes directly from Einstein's general relativity. When physicists solve the equations describing black holes, they find that the math also allows for a reverse solution, a region of space-time that can only emit, never absorb. In simple terms, if black holes are cosmic drains, white holes would be cosmic fountains. How white holes emerge from relativity. The simplest black hole model, the Schwarzschild solution, doesn't just describe a collapsing object. When extended mathematically, it reveals a full space-time structure that includes a black hole, a white hole, two separate regions of space-time, a theoretical bridge between them, a wormhole. This structure is sometimes called the maximally extended space-time solution. Here's the key point. White holes weren't invented for science fiction. They fall out of the math automatically. But physics doesn't stop at math. Why have we never seen a black hole? If white holes are allowed by relativity, why haven't we found one? Because they have serious physical problems. They violate thermodynamics. White holes would decrease entropy. Black holes increase disorder. White holes would reverse that process. That goes against the second law of thermodynamics, one of the most reliable laws in physics. They would be extremely unstable. Any tiny interaction with the outside universe would destabilize a white hole. A single particle falling in would disrupt it. It would likely collapse instantly. In other words, a white hole couldn't survive a real, messy universe. No known formation mechanism. We can understand how black holes form. Massive stars collapse, gravity overwhelms pressure, a black hole forms. But for white holes, there's no known natural process that creates one. They would have to already exist from the beginning of the universe or arise from unknown physics. That's a big red flag for most physicists. The wormhole connection. White holes are often linked to wormholes. In theory, a black hole could be one end, a white hole could be the other. Matter falling into the black hole might emerge from the white hole elsewhere. This idea is appealing. It suggests cosmic distortion, cosmic shortcuts, or even gateways between universes. But there's a catch. The wormholes predicted by relativity are not stable, not traversable, and likely to collapse instantly. So while the connection is elegant, it doesn't correctly describe something unusable or observable. Could white holes explain anything we see? Some scientists have speculated that white holes might explain certain mysterious phenomena. Gamma ray bursts. These are incredibly powerful explosions observed across the universe. Some have proposed a white hole event could look like a sudden burst of energy, but so far gamma ray bursts are better explained by collapsing stars, neutron star mergers. No evidence points specifically to a white hole. The Big Bang as a white hole. One of the more intriguing ideas, what if the Big Bang was a white hole? In this view, our universe could be the output of a white hole, possibly connected to a black hole in another universe. This idea appears in some speculative cosmological models, but it's far from established science. Still, it shows how white holes push us to think bigger about cosmic origins. Quantum gravity and modern ideas. White holes have seen a bit of a comeback in modern theoretical physics. Some quantum gravity models suggest black holes might not end in singularities. Instead, they could bounce, eventually transforming into white holes. This idea appears in approaches like loop quantum gravity. In this scenario, matter falls into a black hole, compresses to extreme density, then re-expands as a white hole. If true, black holes might not be eternal prisons, but delayed releases. That's a wild shift in perspective. Are white holes real? Here's the honest, grounded answer. White holes are, allowed by Einstein's equations, useful in theoretical physics, connected to deeper questions about space-time. They are also never observed, likely unstable, not supported by current evidence, possibly unphysical in the real universe. Why white holes still matter. Even if white holes don't exist, they're not a waste of time. They force physicists to confront the limits of general relativity, the nature of time symmetry, the connection between gravity and quantum mechanics, the true fate of matter inside black holes. In other words, white holes are less about what exists and more about what's possible. The bigger picture. Astronomy isn't just about observing stars and galaxies. It's about testing and boundaries of reality. White holes sit right on that boundary between math and nature, between theory and observation, between what we know and what we don't. And history has shown something important. Most people don't avoid these topics because they're unimportant. They avoid them because they're uncomfortable, and that's exactly why we're talking about them. Tune in for the next episode.